So the reason we have these trig identities is because using them we can simplify a lot of trig expressions and also a lot of trig equations because they all relate to each other. So first, kind of one of the go-to rules you can use is that all 6 trig functions can boil down to just sine and cosine. So the reciprocal functions, secant can turn to 1 over cosine, cosecant can turn to 1 over sine. With the quotients, tangent and cotangent can turn into sine and cosine. So from all 6 trig functions, we can always bring them down to just 2. So in this first one, we're just looking to simplify. Whereas if we use our reciprocal trig function, or trig identity, we know that secant of x is the same thing as saying 1 over cosine of x. Also, we know cotangent of x, if we use the quotient identity, is the same as saying cosine of x over sine of x. So the first thing we're doing here is just rewriting both of these trig functions in terms of sine and cosine. Now, if you notice, if we look straight across, there's a cosine both in the numerator and the denominator. So those can just cancel. So that means if we multiply, this is the same as saying 1 over sine of x. And then we can simplify even further. We know that 1 over sine of x, using reciprocal identities, just equals cosecant of x. So we can simplify those 2 trig functions multiplied together. They really boil down to just cosecant of x. For the second one, we're going to look at Pythagorean identities. Whenever you see something squared, you should always think Pythagorean identities. So as we look at these, first we're going to look at the secant squared of x minus 1. Well, if we think one of our trig identities says that 1 plus tangent squared x equals secant squared x. Now we need to rearrange this a little bit to say secant squared x minus 1. So we can rearrange this just like an equation, subtract 1 from both sides. That means that tangent squared x equals secant squared x minus 1. So now we can just use straight substitution. We have secant squared x minus 1 over there, so we can change that to just tangent squared of x. Cotangent's still there. So now we have 2 options. You can either notice that tangent and cotangent are reciprocals of each other, or we can just switch everything to sine and cosine. If you're ever stuck, always think about switching everything to sine and cosine. And if we do that, using the quotient identities, we know cotangent is cosine over sine. We know tangent is sine over cosine. So now if we multiply these, notice the cosines cancel, the sines cancel. So if everything cancels out, we're just left with 1. So instead of writing cotangent squared x times secant squared x minus 1, that really, no matter what angle we would plug in for x, would always just equal 1. So with that simplifying, it's hard to know what the end game is, like where you're trying to get to. So what we're really working up towards is verifying trig identities. And what that means is this identity in purple here, I'm telling you it is a trig identity, it's a true statement. When a problem says verify it, that means you need to prove that both sides of these equations are equal, but the main cardinal rule is you cannot move terms from one side of the equation to the other. All you can do is use trig identities and use algebra, so combine like terms, get a common denominator, factor if need be, in order to show that these 2 sides are equal. So, for example, on this first one, we have secant squared x minus 1 over secant squared x. Somehow is going to equal sine squared x. Our goal is to show how that happens. So, whenever you see a square, like I said on the previous slide, you should think towards Pythagorean identities. So, the secant squared x minus 1 is the same one we used for simplifying before, where we know that tangent squared x plus 1 equals secant squared x. So, therefore, we know that tangent squared x equals secant squared x minus 1. So we can replace that whole secant squared x minus 1 with just tangent squared x. And again, we're trying to get this in the end. This should say sine squared equals sine squared. So now, whenever you're feeling stuck, remember all trig equations, you're going to use this in a majority of these identities, can break down to just sine and cosine. So at this point, tangent and secant cannot relate to each other how they are. So we want to change them to be in terms of sine and cosine. So using quotient identities, we know tangent is sine squared over cosine squared, big fraction. Using reciprocal identities, we know secant, or we know, we know secant is 1 over cosine squared of x. So again, end goal is to get to sine squared x. Whenever you have a fraction divided by a fraction, here's part of the reason I've stressed this so much this year, you multiply by the reciprocal. So now we know this turns into sine squared x over cosine squared x, top stays the same, times cosine squared x minus 1. And now you should start seeing come together. Here's where we can just use basic algebra. Cosine squared on top, cosine squared on the bottom cancel. Anything divided by 1 is itself, so we're left with sine squared x equals sine squared x. So it took us 4 steps to prove that that identity was true. For this next one, as we start out, there aren't any squares to deal with, so we know Pythagorean identities will not help us. Again, the terms have to be squared for Pythagorean identities. So we're looking towards reciprocal and quotient identities, which means, in this case, we can't relate anything as is. We need to turn everything into sine and cosine so that we can relate it to each other more. So sine is already sine. We'll just keep that as sine of theta. Cotangent, if we use our reciprocal identity, we know cotangent is equal to cosine over sine. And cosine's already in. Sine and cosine, I'm going to change it as cosine over 1, just so that we can compare it to that fraction again. And we aren't going to be touching that right side of the equation. We're just trying to show that the left side can boil down to cosecant. So from here on out, we don't really need to use any identities for a little bit. We just need to use algebra. So first, we're going to want to simplify this whole fraction mess here. And if we have fractions, you multiply straight across. So this turns into cosine squared theta over sine of theta. The rest of this stays as is. Now, we have 2 things being added together, and we know in the end we should boil this down to 1 term. Well, if that's ever the case, then we need to actually add these terms. Well, to add fractions, that means you need a common denominator. So in this case, our common denominator will be sine. So we need to multiply this first fraction by sine over sine. So this turns into sine squared theta over sine of theta plus cosine squared theta over sine of theta. And again, we're still trying to get it to cosecant. Now that we have a common denominator, we can actually add these fractions. So remember, when you add, you just add across the top. Bottom stays as is. So this turns into sine squared theta plus cosine squared theta, all equal sine of theta. Now we need to think back to identities. Something should look familiar in here, especially as you get used to these. Just earlier today, we came up with those Pythagorean identities. Remember, the basic Pythagorean identity says that sine squared plus cosine squared always equals 1. So we know sine squared plus cosine squared on top just equals 1. That means now we have 1 over sine of theta equals cosecant of theta. And now you should notice this is just a reciprocal identity. We know 1 over sine equals cosecant. So cosecant of theta equals cosecant of theta. There are always multiple ways to do these identities. The whole goal is it's a proof. We are proving that the identity I'm giving you on top, again, I'll never give you a false statement up there, that they will always work. We are proving and showing how those 2 sides are equal to each other. So we're using our different sets of identities and substitution and then just simplification to show that what we start with on top can boil down to just two equal sides of the equation. You will always have to show each step. You cannot skip steps. We know what the end goal answer is going to be. The whole point of the problem is all of this work in the middle. So there are two of these for you to try on the next page. Just keep in mind hints of changing things to sine and cosine and getting common denominators to add all your pieces together. Try your best. I know this is strange, but think of it like a puzzle. As you get used to it, it's just a matter of how can I show these two things are equal to each other.